Good morning, myself Sanjeev Kumar. Today in this lecture we are going to discuss about efficiency and what is the condition for maximum efficiency. We know that DC machine having mechanical input, DC generator having mechanical input and electrical output. So the efficiency may be called as the ratio of output power to the input power. That is, efficiency is output power by input power. So this is the efficiency is nothing but output power by input power. Is the ratio of output power to the input power. But in power stages, as already we discussed, that we are having the three stages. So what are the three stages? A is the generator input. This is the first stage. And the second stage is mechanically equivalent electrical power generated or electrical power generated B. After the reduction of iron and mechanical losses from the generator input, we will get the mechanically equivalent electrical power generated in armature, and the third one is electrical output. And from the second stage, we are deducting the copper losses. After that, we are getting the electrical output power. Now we are having three stages, so we have to take out the mechanical efficiency as well as electrical efficiency. So mechanical efficiency is given by second stage by first stage, nothing but B by A. So what is meant by B? B is nothing but electrical power generated, which is equal to mechanical equivalent. So this mechanical efficiency, so this is a symbol of efficiency eta. Eta M, subscript M stands for mechanical efficiency is equal to electrical power generated divided by generator input. Now this is the mechanical efficiency. Why the input is always mechanical input from the petrol engine or diesel engine or turbine. So that's why the generator input is mechanical and it is the mechanical equivalent electrical power generated in armature. And the second one is electrical efficiency. Now after the first and second stage, from the second stage we are going for the third stage by second stage. So what is the third stage? It is nothing but output. Electrical output by second stage is mechanical equivalent electrical power generated in armature. So after the second stage, again we are deducting the copper losses, we are getting the electrical output. Now the formula is eta subscript E, it stands for electrical efficiency is equal to electrical output by electrical power generated. Now this is the efficiency for electrical. Now the total efficiency from the input to output, why the efficiency definition is output power by input power. Now the overall efficiency or total efficiency, you can also call it as sometimes commercial efficiency, is given by total output power to the total input, that is means from primary stage. So which is equal to last stage, third stage electrical output by first stage mechanical input, nothing but generator input. So eta is given by C by A. What is C? C is nothing but electrical power output divided by generator input. Now you can see here output input. Now in simple sentence we can written as eta is equal to output by input. So it stands for total efficiency. Now output by input, but this output can also be expressed in terms of output plus losses. So input may be expressed in terms of output plus losses. While generator output power is electrical and input power is mechanical. So it is easy to make the calculations. If you know the output power, then you just add the losses to the output power, you will get the input power, then you can calculate efficiency very easily. So the overall efficiency is equal to electrical output power by electrical output power plus losses. So there are stray losses plus copper losses and overall losses, total losses, three major losses we will add here. We will get the efficiency, and this efficiency is less than 100%. So you can calculate in terms of percentages. This efficiency is less than 100% because the output power may not be equal to input power until it is a ideal machine. So without losses, the output power, but each and every machine having some losses. So this efficiency is always less than 100. Generally DC machine having 90 to 95% of the efficiency. In commercial applications it may vary from 85 to 95%. So by reduction of losses makes the improvement in the efficiency. So by using good conductors we can reduce the copper losses. By using the good material we will decrease the hysteresis losses. And choosing the making the laminations will make the reduction in eddy current losses, and with proper maintenance, proper lubrication, greasing will reduce the mechanical losses. This is about electrical efficiency. Now we will see what is the condition for maximum efficiency. Now we will see the condition for maximum efficiency. We already discussed that efficiency is nothing but the ratio of output power to the input power is called as efficiency. Then how this efficiency is improved to maximum value so that losses will be reduced and the machine runs at the higher efficiency. Now here is the condition. So condition for maximum efficiency, let generator output power is equal to VI watts, nothing but it is electrical output power, and generator input is output plus losses. So what is the output power? V into I, and I square RA is the copper losses and WC is the stray losses. Stray losses includes mechanical plus iron losses. Now this copper losses and this iron losses added together, and this will be added to output power. You will get the generator input power. Now what is the efficiency formula? Output power by input power, so that the output power is V into I by VA plus I square RA plus W subscript C, nothing but stray losses plus copper losses plus actual output power. So this is output by output plus losses formula. So what is the formula? Output by output plus losses. So output by output plus losses. So always in generators we are coming from the output side. So whereas in motors we are coming from the input side, whereas electrical power is very important to calculate the efficiency. That's why the actual electrical output power is output side. So we are coming from the output side, output plus losses, so that we will get the input. Now output is VA and these are the losses. So efficiency is VA by VA plus IA square into RA plus WC. And here is some simple assumption I am making. Since ISH I am assuming it is very small, so that I can written as I square RA, IA square RA. So IA and I, so like that the load current I am assuming as armature current, since shunt current is very small. And from the efficiency equation VA by VA plus IA square RA plus WC, dividing numerator and denominator by VI, now we will get efficiency is equal to 1 by 1 plus IARA by V plus WC by VA. Now this is the efficiency equation. Now for this we have to maximize. That means we have to improve the efficiency and we have to decrease the losses. What is the condition for that? We are going to derive. Now if you see this term, the numerator is 1, the denominator is having some expression IR, AYV plus WC this. Now if you further decrease this denominator, then the efficiency is going to increase. Why? This efficiency and this denominator term in inversely proportional manner. So if you decrease this term, the efficiency can be increased. Now how we are going to decrease this term? That means you have to minimize this. The efficiency is going to maximize. Now how this term is going to minimize? So for that, a mathematical method we can call it as differentiation. By differentiating this denominator and equating it to 0, we will get the condition for maximum efficiency. Now see here, to obtain maximum efficiency, the denominator should be minimum. Therefore, differentiating denominator with respect to I and equated to 0. So, we are differentiating with respect to I. Since I is the very important, since it is a major factor current in calculating the losses, copper losses, and Ra is equal to constant armature resistance. It is a very small, and the constant losses are anyhow constant irrespective of the load, but only current is going to change always with respect to load. So that's why I am differentiating with respect to current and equating it to 0. Now what we will get? Differentiation of this term with respect to I and equated to 0. Now the differentiation of constant is equal to 0 and differentiation of I into Ra by V. So I will get Ra by V, and the denominator we are having I 1 by I. You know differentiation of 1 by x minus 1 by x square like that. So WC by minus V into I square. Now this term is 0 and we are getting one negative term. You take into right hand side, we will get the positive term. So WC by V into I square equal to Ra by V. So V both terms gets eliminated. We will get I square Ra is equal to WC, or IA square Ra is equal to WC. Now this is the condition we will get from after differentiating. Now what is this condition? Constant losses equal to variable losses. While you are loading the generator, you are getting a point at that constant losses are equal to variable losses. Where you are getting constant losses as variable losses, then your efficiency is going to maximum. So this is the condition for maximum efficiency in DC machines. So you have to adjust the armature current. It is the losses, the copper losses equated to the constant. So this is constant losses. Variable losses is equal to constant losses. What are the constant losses? Iron losses plus mechanical losses. And if it is a constant motor, you can also call it as a shunt copper losses also we can include. So armature current has to be adjusted like that. Constant losses is equal to variable losses. Now we will get the maximum efficiency. So this is the condition for maximum efficiency, and it is very important question in our exam point of view. To remember this condition, and we have to solve the what is the current related to maximum efficiency and what is the condition for losses for maximum efficiency, and where you are getting, at which load you are getting the maximum efficiency. So some different numerical problems also we are going to solve in next classes. So this is the condition for maximum efficiency. Now we will make the problems on efficiency. Now to calculate efficiency we require input power and output power. So generally we are coming from the output power since it is a electrical power. Now this is the first problem. Now the question is a 4-pole DC shunt generator delivering 20 amperes at 200 volts. If armature resistance is 0.5 ohms, shunt field resistance is 50 ohms, calculate the induced EMF and efficiency of machine if stray losses are 464 watts and assume 2 volts per brush drop. Now basically it is a DC shunt generator, load current is given and load voltage is given, so armature resistance and shunt field resistance are given. Now you have to calculate induced EMF and efficiency of a machine by taking stray losses are 464 watts and brush drop of 2 volts. Now we have to calculate the total losses. Since stray losses are given, copper losses we have to calculate. We have to calculate the brush drop losses. To calculate the copper losses, we have to find out first armature current. Then we will go for the generated EMF as well as losses and efficiency. Now, for the solution, write the given data first. Now the given data, a DC shunt generator having number of poles. So how many number of poles are there? 4 poles. Load current. So the load current, it is nothing but pi L is equal to 20 amperes. Delivering means output power. Output is nothing but load current and load voltage, which is nothing but VL is equal to 200 volts. And also armature resistance. Armature resistance. So armature resistance RA is equal to 0.5 ohms and shunt field resistance RSH is equal to 50 ohms. Now it is going to be higher value, 50 ohms. And stray losses are given. Stray losses is equal to, we can also take it as WC is equal to 464 watts and brush drop is given. So brush drop is 2 volts. Now what we have to find out? We have to find out generated EMF and also efficiency. Now first of all we have to calculate the currents, then it is easy to calculate the generated EMF so that we can calculate the efficiency. We already calculated problems on generated EMF. First of all we have to find out the currents. Now see, the load current is already given. Now we have to find out shunt current and from that we will find out the armature current. So we have armature current IA is equal to IL plus ISH. Now since it is shunt generator ISH is equal to V by RSH. Why? Shunt winding is directly connected across the load, so load voltage is same as the voltage across shunt. Now what is the load voltage? 200 volts and the shunt resistance resistance is 50 ohms. Now we will get 4 amps. Now shunt current is 4 amps. The load current is already given 20. So the armature current, therefore armature current is 20 plus 4, 24 amps. The load current is given 20 plus 4, 24 amps is the armature current we are calculating. Now what is the generated EMF formula in terms of armature current in shunt generator? So the generated EMF given by Eg is equal to V plus Ia into Ra plus brush contact drop voltage. Now what is the V again? Once again V is equal to 200 plus Ia is now 24, and what is Ra? Ra is nothing but 0.5 multiplication, and brush volt drop is 2 volts. Now what is the voltage we are getting? 200, half of the 24, 12 plus 2, 14. So we will get 214 volts as generated EMF. Now the generated EMF is calculated and armature current is calculated. Now we have to find out efficiency by using these currents and by using the stray losses are given. Now what is the efficiency formula? Now to calculate efficiency, all the losses has to be determined. Now what are all the losses? Armature copper losses, shunt field copper losses, and brush losses, and you have to include the stray losses. Now we will calculate one by one what is the losses for by using armature current, load shunt current, and also brush drop. Now this is the given data and this is the solution. I am going to take out this so we can calculate the losses. Now armature current is 24 volts and Eg is 240. I am going to take off this data. Now one by one we will calculate the losses. Now first one is armature copper losses. So which is nothing but Ia square Ra. So what is Ia value? 24 square into Ra 0.5. So since 24 square is 576. Now 0.5 is nothing but 288 watts. Now this is the armature copper loss. Similarly, shunt field copper losses. Shunt field copper losses is nothing but ISH square into RSH or V into ISH. Now we will take out V into ISH is equal to 200 into 4. Shunt current is 4 and V is equal to 200. So we will get 800 watts as the shunt copper losses. Now armature copper losses are completed, shunt field copper losses are completed. Now brush losses. Now brush losses is calculated by V, sorry, I into brush contact drop. So this is armature current since it is connected to the commutator segments where armature current is delivering. So armature current into brush contact drop, which is given by 24 into 2. So which is nothing but we are getting 48. So there should be in losses. So we will get brush losses are IA square into VC. So 24 square into 2, which is nothing but 1152 watts. Now once we will get the brush losses, armature copper loss and this, now we will add all these to this particular one. Now we will get the remaining, sorry, this is 24 into 2, 48 watts. So 48 we will get the, and what are the remaining losses? So these losses are calculated for armature, shunt field and also brush losses. Now what is the total losses? So total losses is equal to IA square RA plus ISH square RSH plus brush drop I into BCD plus stray losses.